it's a pleasure to start the year with our first seminar from Sasha Kiselev. He's visiting us from Duke and is going to talk about the regularity of patches, Vortex patches and SQG patches.
Yeah, thank you so much. I think some of you have heard this talk. It will be close to what I've talked about at AIM, but hopefully in the end there will be a little bit new things. So everything I'm going to talk about is joint work with Xiaoyutao Luo. And the family of equations that I talk about can be written like this. So U is given by Xiaoyutao Luo like that. So the setting, let's just think about the whole plane. So it's an R2. And alpha is a parameter which will be between 0 and 1. So alpha equal to 0 is just 2D Euler equation. And alpha equal to 1/2 is what's called the SQG equation, comes from atmospheric size. And in general, in between, sometimes these equations are called modified SQG equations or generalized SQG equations. So they sort of interpolate between these values. And moreover, I'll be interested in a specific class of solutions. They are called patch solutions. So these are weak solutions, and they are given by characteristic function of some evolving region. And so in general, I mean, these are weak solutions, so even like existence is not immediately clear if you start in such class. Like for Euler equation, the fact that such solutions exist and are unique is a consequence of Udovich theory. So Euler, well, at least if we start with, for example, a compact region in the beginning. So patches exist by Udovich theory. But the kind of question that I will be interested in is what happens, can there be singularities, qualitative properties of evolution of a patch? And so in this context, the regularity question, like global regularity of finite time block, refers to what happens with the boundaries. Can one form corners or cusps, or maybe different patches can collide? So these are all would be kinds of singularities. And actually for Euler, finite time blow up has been conjectured by Maida based on numerical simulations. And
what kind of blow up is it?
I think it was formation of a corner that the numerical simulation that Maida, the numerical simulation, I think it was by Butke, but then better resolved numerical simulation showed that there is no finite time blow up. And in fact, Chemin in 1994 proved global regularity. And that was done in CK alpha in the Hölder spaces.
And that also means that two patches cannot.
Yeah, and two patches cannot collide. Yeah, so.
The patch does not need to be topologically trivial. Could have holes inside, right?
It could be several patches.
Yes, and it could be like.
But I think like for Euler case, the fact that they don't collide follows from Udovich theory. So that because trajectories cannot, right, cannot cross. There's log Lipschitz bound on velocity. And so but it's not obvious from Udovich theory that you can't have cusps or corners. And I think that's what numerical simulation suggests. And so global regularity for Euler patches has been established back then. Now, for alpha SQG, the story becomes more exciting in the sense that, like even for smooth data, as soon as you depart from this alpha equal to 0, global regularity is not known. And defining patches proving like existence and uniqueness locally for SQG and alpha SQG patches is not straightforward. So when you look at alpha SQG, I think first result, like local regularity and uniqueness, if you start in sufficiently nice class, I think first result was by Rodrigo. I'm guessing maybe around 2000 or something like this. And this was in C infinity class. And then Gancedo did it in H3 in Sobolev class or higher. On the other hand, there have been some numerical simulations that for alpha SQG suggested that there could be finite time formation of singularities. So, numerics, I think the first one was by Cordoba, Pontelis, Mancho, and Rodrigo. And they started with 2 patches. And in their numerical simulations, what they saw is that the patches develop sort of arms like this, and then they touch each other, appear to touch each other. And at the point of touch, curvature becomes infinite. Okay. And then there is also numerics by Scott and Ritchell. And in their numerics, they start with a single elongated patch. And then what they see happens is that there is a thin filament forms between 2 lobes. So patch evolves into a picture like this. And then after a short while, if you zoom into this region, you see the same thing. So they observed a cascade of sort of structures like that, and over geometric sequence of times, it leads to singularity. And there are 2 papers. The first was a cascade like this. And in the second one, they actually conjectured that finite time pinch-off could also happen. So you could have a situation where you actually get something like this. So this just gets pinched off, this thin. My filament was going that way in the picture. So, but your modulo that's the picture that you're gonna see. So you have a patch and another thin filament, and it gets pinched off in finite time. And so this all suggests that finite time singularity may be possible. There is one result on formation of finite time singularity for alpha SQG patches. So that was due to Rijik, Yao, Zlatish, and myself. But we needed boundary to make it work. So there was a half space setting. And we start with odd initial data like this. And then what we think happens is these lobes shoot out thin filaments which meet at the origin and simultaneously create a singularity in the curvature.
But that is not a patch according to your definition, though. Or am I missing something?
Why not?
because you're saying it has to be the characteristic function of something, so it cannot take a negative value, right? Or...
Yeah, you're right. Well, let me put a constant here.
Okay.
Well, if I wanted to be more general, like I took the simplest kind of a patch, and that's what I will be concerned in this.
So you have a number of patches with different values. Okay.
But yeah, I didn't want to write more, but in reality, yeah, you could have a sum, a finite sum of disjoint.
Okay, I understand.
Sufficiently nice domains. So you can still build the whole theory for these classes. That's fine. And
Shaman wouldn't be affected by that either.
No. So I think it all works for such combinations. So here our constraint was that alpha is actually between 0 and 24. So it's a kind of funny constraint because, you know, you'd think for more singular models should be easier to show blow up, but with more singular model, you have less control. So it doesn't work that way. And we proved it in this case. And then later, Gancedo Patel extended this range up to 1/3. But this involves boundary, and in some sense, it's a little bit different story. So boundary is essential in this construction. And so one thing that kind of repeats over all this scenario is that it seems that what happens is that curvature blows up. And indeed, and patches collide as well. And so, in fact, in order for patches to collide, it is known that curvature has to blow up. So, for collision, one needs, well, curvature or even some weaker norm for small alpha to blow up. In particular, where is that smell? Yeah. So no splash, no something that is called splash singularities. So I'll say a few words about it. So no splash singularities. For some fluid models, you can have this, right? So like for water waves, you could have just without singularity, two interfaces collide, but not for SQG patches. And so this result goes back to Gancedo and Patel. Sorry, not Gancedo, Gancedo strain. And we improve slightly on the result. So what one can show essentially is that, well, you assume you have a kind of splash picture. So let's say P and Q are closest points on the interface, and it's a splash, meaning that locally, that's all you have. You don't have a too complicated picture, right? That's what's called a splash. And then one can prove a bound on the distance. That distance is actually greater or equal than initial distance, and then exponential of minus the something like C11 norm of the interface. And this works up to 1/2, but for it, yeah, I think that includes also SQG case, yeah. So, but not beyond that.
Is this local?
This is local. This assumes, so you assume that your scenario is like this, that at any time,
the C11 norm is only on
yeah, some fixed ball.
Okay.
Yeah, some fixed ball, and you have in this small ball a picture where there are just two interfaces. Maybe you can allow it to shrink a little bit as distance becomes smaller. but yeah, you assume this local picture, and then you can prove such bound. And essentially, what compared, like Gancedo strain had a similar result, but a little bit with double exponential instead of single exponential. And the observation that allows this improvement is basically that there is, the Xiaoyutao Luo is odd with respect to this axis. And so you essentially get cancellation when you do a reflection. So it like I reflected, and this part will cancel with this one, and this will be the only one that will remain. You'll have to integrate about. And same thing here, this one will cancel with this one will be the only one that remains. And that creates extra cancellation, and then you can obtain a bound like that. So I should say also that at the same time as our work, John and Zlatish proved actually that for alphas between 0 and 1/4, there is just no splash singularities. So they don't even assume that the picture is like this. They can allow layers, so a little bit more complex geometry. So it's a little bit more robust result, but in the restricted range.
With the same C11 assumption.
Yeah, with the curvature assumption. Well, it depends on alpha. So I think it's like C minus 1 to alpha. Mm-hmm. Yeah, so you can put here a better space if your alpha is smaller. This works all the way to 1/2. Okay, so this all kind of brought us to a thought that it would be nice to write evolution equation for curvature, because curvature seems to be relevant in these problems. And so we wanted to write evolution equation for curvature and see what will come out of it. And we were hoping that one could maybe understand singularity formation out of this equation. And we couldn't do that so far, but something else came out of it, which is entertaining. And so I'm going to tell you what came out of it. So write equations for geometric quantities. And these geometric quantities, right, before I start with that, I have to use some notation. So we'll parameterize, we'll look at a single patch and parameterize it by a map from labels into R2. And then the patch evolution can be reduced to something called contour equation. So the evolution equation for patch can be written in this form. So for Euler, it will be a log here. And for alpha SQG, it will be a power more singular expression minus 2 alpha. With some constant, which is not important front. So this is just integration by parts. One writes this Xiaoyutao law. You integrate over the patch, but then you integrate by parts and reduce things to the boundary. That's, as far as I understand, one of the reasons that engineers actually like patches. So I talked with some engineers, and they, like atmospheric engineering, they actually like to simulate patches because it's so cheap. It's essentially one-dimensional integral that you are taking.
This would be a single patch.
That's a single patch. Yeah. And, yeah. So we'll think about single patch. And so now we'll introduce the arc length. And the curvature. And well, one way to think about the curvature is that, right, we have a tangent and normal. And if we move along parameterization, that's how the tangent vector changes, and that's how the normal vector will change. And this kappa is curvature. So then you can write evolution equations for these two quantities. And yeah, one more thing that will be convenient for me to use is that, so Xi is labels parametrization. Xi lives just on its circle, and alternative is arc length. So by S, I will denote arc length parameterization. And so you can make a computation, and right, if I call all this expression V, right, so this is velocity by which patch is vectored. So it will be, or in arc length, can write it like this. And the curvature equation will be like this. So it's just a computation. These formulas are well known for differential geometers, and in fluids they've also been used, but as far as I know, never for patches. So I think for Hellish-Shaw problem and for waterways, they've been used by Tom Howell, Low and Grubb, and Mike Shelley, and by some other people. But for patches, I don't think that they've been looked at. And so this is the key equations that we are going to look at. Maybe I will write expression for the derivative of velocity, just to have it in front of us. Maybe it will be useful later. Okay, so it will be something like this. Then let me do S, just adjust by G. Okay. And so let me first talk about Euler, because even though Euler, we know it's globally regular, nevertheless, there is something new that came out of these equations for Euler as well. And so first, let's think about Euler, alpha equal to 0. So here's a couple of theorems that we prove. So assume omega 0 is in W to P, and P is between 1 and infinity. So then there exists unique solution. W to P solution. So as far as I know, it hasn't been previously known, like CK alpha results for regularity spaces used for Euler patches. But there's nothing too difficult about the proof of this theorem. So I won't say much about it. And then the next theorem is more interesting. So there exists omega 0, which are in C2, such that the solution omega CT, well, it will be in W to P for any P, for any time. But it will not be C2 for times which are not integer. for all times that are not integer. But for all integer times, it will be C2. So for all t which are integer, omega ct will be coming back to C2. So it immediately loses C2 regularity, but then every integer time it remembers that it was once nice and becomes C2 again. And it's not time periodic. So it does completely what it wants to do. And so what's behind this theorem is curvature equation. And let me write a proposition that would be important for proving this theorem. Suppose gamma Ct is in W2P, P is greater than 2. So then, the way we can represent the curvature equation is in the following fashion. So there is a multiplier term, and then there is a explicit term that's really at the heart of this phenomenon. It's a Hilbert transform term. And one more term. And so here A is in C sigma. Sigma is 1 minus 1 over P. And F is C beta. Beta is 1 minus 2 over P. But still it's Herder class because P is greater than 2. And H is periodic Hilbert transform. And so for that reason, it's the most singular term in the equation. All right, so H. So that's the structure of the curvature equation. Okay, so let me say a few words about how one proves it and how it comes out of that equation that's written on that side. And so for that, let me write what you actually get when you carry out these differentiations in the curvature equation. So, right, so let me put it here. We can compute that the curvature derivative of curvature. Now, there's a couple of steps between these formulas here and what I'm going to write. So it may not be immediately clear how one follows from the other. Okay, so this will be this A. Okay, so A will come out of this term. And then, of course, there will be terms coming out of these derivatives, the second derivative of V there. Okay. That's one term. That's second term and the last one. I think that's okay. And so let me try to convince you that this is believable based on these formulas. Okay, so I can sketch up the proof. Which term do you think leads to Hilbert transform?
Value.
Yeah. I should have put principal values here. Make it less obvious. But yeah, so this is one, right? Product of normals, right? It's W2P, therefore the normal is actually Hölder. So to the main order, the product of normals will be 1 plus something Hölder. And the part that appears in the numerator, it's going to be Xi minus eta to the main order, right? Times GC, right? So then plus, again, something that is of this order, or maybe even better. And denominator, the difference of gammas will be like G squared C minus A squared. And so when you take the main orders, you get exactly Hilbert transform kernel. Right, you get Xi minus eta over Xi minus eta squared, which is essentially singularity that we have here. And so this term will lead to Hilbert transform, and the rest will be more regular. And it turns out that one can put it into this F, which is Hölder regular. And just to give you maybe a little bit more of kind of flavor. This, let me write why the third term is better, how to see that the third term is better. And so in the third term, this dot product will be O of Xi minus eta sigma, because T and N will be orthogonal when eta is at Xi. And then the term in the numerator, right? We can actually write the difference of tangent vectors as integral of the normal vector. Okay, and so to estimate this, like I'm not sure that in this term we actually need to do this, but in maybe in the next one we definitely need to do this. So the way we will estimate it is this product is again Xi minus eta sigma, so some constant Xi minus eta sigma, and we will use maximal function estimate. So the integral in here, G is L infinity, it's C1 alpha, so it's L infinity. And then here I will put maximal function of curvature. And then when we plug it back into this third term, so we'll get an integral that will have this maximal function. And then we'll have c minus eta squared coming from denominator, but we'll cancel it with these ones, and we will get something like that. And this is in LP, and at least you can see just using Holder that this is going to be L infinity, right? So it's a little less than what's claimed, but it's clearly better than Hilbert transform of LP function. And with a little more computation, you can get that it's also Holder. So it's this sort of argument. Okay, and so once this proposition is proved, then it's actually a relatively simple argument to prove the theorem. So to prove the theorem, we'll need to do like a little integrating factor argument. So we'll have an integral of this a c tau d tau from 0 to t times the curvature. And then for this new large kappa, the equation we'll have is pi h large kappa plus a commutator, or minus, I don't know. Okay, doesn't matter. Minus. So from 0 to t, applied to kappa, and plus this f ct e minus a c tau d tau. And now because a is Hölder, f is Hölder, so this whole thing is c beta. And there's a commutator estimate you need to do, but this object will also be in c beta. So if kappa is in LP, this will also be in c beta. And so with that, we just have a Duhamel formula. Right, so then the large kappa is going to be just E PTH kappa 0 and plus E PTH T minus T prime, and then something which is C beta, ET prime. Hilbert transform preserves C beta, so this will be C beta. But now this exponential is actually just cosine pi t plus h sine pi t. Right, so this is since Hilbert transform squared is -1. And so that's what drives this return to regularity, is for all integer times, this term will just vanish. And we'll just have a constant there. And the kind of initial curvature for which this happens is actually can be quite explicit. So for example, all we need to do, right? So for example, if we take kappa 0 to be minus log C minus 1, minus 1/2, if C is between minus and 0, and then log C minus 1 minus 1/2 when C is 0 epsilon. Then in fact, what we have is that kappa 0 will be continuous. But if we look at Hilbert transform of kappa 0, look at its LP norm, it's greater or equal than constant times square root of P. Okay, so in particular, it's not L infinity. And then with such kappa 0, Hilbert transform will kick us out of continuous functions. But it will remain in any LP.
So let me ask the question. So this proves global regularity like Chemin, right?
W2P.
W2P, right. But I mean, it definitely proves that if you start with, say, a C1 patch.
C1 is a little.
No, W2P. I mean, like say, I mean, if it is regular enough, it's a little bit better than C1.
C1 scares me.
Right. Okay. So let's say, I mean, if
but you're right.
If the patch is C2, it will keep being C1 alpha at least.
That's correct. Yes.
And so there's not going to be any singularity. So how difficult is if I were, I don't know, once I have this information, if I want to bootstrap and get Chemin?
Well, we actually used Chemin to prove this result globally. So the Chemin, well, maybe not quite Chemin. We use a trick from Bertozzi-Constantin version for the same result. So our W2P result relies on that result.
Now I've lost you because you just get an a priori estimate. Why can't you simply run it for ever?
It's, well, I didn't say anything about proof of theorem 1, but a priori estimate that you get there is not global. It will give you local, it's a fixed point argument. So you get local thing, and to continue it, we just used the CK alpha, C1 alpha.
Ah, you mean like you're hiding the fact that these things are C beta, you're hiding.
Yeah, these are very strongly nonlinear things.
Okay. So there's C beta as long as the other things are under control, but then you're just saying like, okay, I have multiplications and then I can't simply, so it's going to be true only locally. So when you want the global thing, you still have to use Chemin. You're not providing any alternative to that.
Yeah, we're not.
Okay.
I don't know, maybe we could, but it wasn't obvious. So we didn't, try.
I understand.
It was a fixed point argument. Yeah. Okay, so that's the Euler story. And but I should have said, then I forgot to say, that ill-posedness results for Euler, of course, it's not new. It's new for patches, but for smooth initial data, there are results on ill-posedness of Euler in CKA and in critical Sobolev spaces that go back to Bourgain-Lee. And Elgindi-Masmoudi. But for patches, the only result that I know of is Elgindi-John paper, where they show that essentially C1 ill-posedness. You start with not quite even C1, I would say, maybe W1 infinity. So you start from an angle and it has to cusp. And so for patches, C2 is new, but I think the kind of, for me, the interesting thing is how it comes out of curvature and the structure of the curvature equation in particular. And so the next natural thing to do is to look at the alpha SQG. And so this is something in preparation. But for alpha SQG, the situation is interesting. It's actually really different from Euler. For alpha SQG, one can derive at least in some range. So for now, we are thinking about this range. Something has to change at 1/2. One maybe needs to do an extra regularization or something like that. So we haven't worked that out yet. But in this range, curvature equation has similar structure. There is again a main term that is linear, right? So it's the case here. But of course, this term has to be more singular, right? It's more singular than Hilbert transform. And the main term so let me now write it like this. For Euler, it is Hilbert transform. Or if we want to look at Fourier side, it's a multiplier I zeta over zeta, and I'll ignore the constants. So it's a Fourier multiplier like this. On Fourier side. And for alpha SQG, it is a pseudo-differential operator.
Does it have a good sign?
Say it again?
Does it have a good sign so you have energy conservation or something like that?
This guy here?
Yeah.
Yeah, I mean, I don't. You see, on this level, it's curvature, so there's no. But this is dispersive, right? So it's not dissipative. So it's.
Zero. Okay.
Yeah. So it's dispersive, and for alpha SQG, it's a pseudo differential operator, which is G Xi minus 2 alpha, and then it's zeta on Fourier side, right? So I'm not now going to do Fourier side. So it's again zeta minus 1, but for a second. Yeah, so it will be again zeta, but here we'll have plus 2 alpha. So it's more singular like that. And I think it's so high. And so it's sort of Benjamin Ono type dispersion.
Wait, what was G again?
Oh, G is the arc length.
Okay.
Yeah. So that's on the coordinate side. And that's Fourier symbol. So if I write it on coordinate side, it will be some convolution. But the interesting thing about this kind of dispersion is that if we simplify it a little bit, like say, okay, G is sufficiently regular, let's ignore it for now, and look just at this multiplier, and like for Hilbert transform, try to see what evolution group of this multiplier, what does it do? So if we take this this multiplier, it's known to be not bounded on LP with P not equal to 2 or CK alpha space. Maybe I should say CK beta space. Okay. So it has pretty bad properties, this multiplier. And this goes back to works of Hirschman a while ago and Wenger, Steve Wenger. And so, therefore, a natural conjecture, which is a little bit informal, is that alpha SQG patches are ill-posed on all spaces except L2 based or C infinity type of spaces. If you ask me Gevrey, then I have no opinion. I don't know. but they are ill-posed on LP spaces. They should be ill-posed on Hölder spaces, which is very different from Euler. So Euler is well-posed on CK beta spaces, that goes back to Schema, and on LP like W2P. That's more recent. But for alpha SQG patches, it should be very different. Okay. So I think we can prove this with some constraints on exponents, but more or less, it's it should be the case. And so, I guess the last thing I want to say is that for the singularity problem, so far we couldn't quite see how this structure can be used to gain more insight. We haven't given up on it, but in a way, I think this linear term is an enemy of blob because it's dispersion. So any blob that you try to construct, you will have to overcome dispersive effects which are produced by this multiplier. And so maybe there is a nice way to understand it, but that's something that so far is open. And yeah, I think I'll stop here. Thank you.
You go ahead.
Okay. Are there some results on infinite time loss of regularity for Euler patches?
It's a good question. So I know that there is an analog of this double exponential thing in a bounded domain. My student did it. I'm less sure. I would imagine that one can do like Nadirashvili thing with patches.
Meaning
that, well, actually, yeah. So yeah, it's not obvious actually. Yeah, because it is not going to be. Yeah, his example is an annulus, and you put something like a shear flow background, and then use stretching to show that you have like infinite growth of derivatives at linear rate as you would expect in a shear. But with patches, I think you're gonna just show that they come close together, right? It's not obvious that you'll create any curvature of that. So I don't know. That's a good question, yeah.
So, Euler's equation. Do you have a sign that kappa is bounded and the higher norms remain bounded if it's bounded initially?
So yeah, so there is you can prove conditional regularity results like that, yes. I think curvature would be sufficient for this range.
For the free surface waterwave problem, Dmitry, Kiselev and I had a result. Essentially, as long as the second fundamental form of the boundary is okay, and there's no domains clashes, then higher norms remain bounded. See similar.
That's right. Yeah. And like this is exactly sort of what we used in W2P global regularity. We just took C1 alpha from Schema, and one can show that then this regularity persists. And I'm actually not aware of a computation written somewhere for higher order norms because it becomes very long, but it should be true, and maybe it's written somewhere.
So you stated everything for a single patch, but your proposition is for any number, right?
For this, for each patch it would hold, yeah, individually. If you're asking if you have so.
Yeah, I mean, you can have many of them, and then I guess your equation becomes, I mean, gets another term, but you're not bothered by that, right? Because you know they cannot get too close.
For Euler, yes. For SQG, that's exactly the very interesting question, because all these numerical simulations, they show that I'm not aware of any numerical simulation which would just show like corner or cusp forming out of nowhere. It's always patches approach, and they sort of induce on each other this singularity.
They can pull back on each other. That was just
Yeah. Either the other one folds like this, or the patch folds on itself, and so that's exactly something to look at. And so it seems to be important that two branches come together very closely, and then the equation will change, because the other branch you have to write what it contributes. And as you approach, it will grow.
But is there a is this just what you can infer from numerics, or can you or is there a proof of the fact that
there is not a proof that isolated singularity cannot form? That's another very nice question.
Yes, this is an open problem.
It's an open problem. Yeah, I think it's a natural conjecture, and maybe this dispersion can help with that. In fact.
But it's not just that this is a single patch. I mean, you also have to like say put a condition which is telling you that there's not like some portion which is far away, which is coming back touching you, right?
Yeah, because it can. Yeah, like in,
because you don't see that. You don't see that simply by looking at the curvature.
Yeah, no. Yeah. Because Scott-Dritchell computation is exactly that. So it's one patch, and then you have formed this filament, and you have a lobe, and this thing comes in. So it's one patch.
Is there any low, say, small data result which would tell you that that doesn't happen in finite time? Say if I start like sufficiently close to a circle.
No, not for circle. I think there is a paper by Alexandru Ionescu and a co-author. Ale. Yeah, it's about half plane. So if you start close to half plane, yeah, then they show results of this type, and I think they have to look at alphas which are worse than SQG, so they have to look at singular alphas.
So you're looking at something which is potentially more singular, but you're proving it's better behaved.
Yeah.
Funny enough.
Well, I mean, as our proof looks at something more regular, it proves that it's worse behaved, right? The block we have is 1 and 24, right? We cannot go higher. But I agree, but I think it's because dispersion is stronger. So you have high power of dispersion.
Any other question? Well, if not, thank you.